So now that we have introduced curl, let's connect it back to Ampere's law. All right, and I'm going to start by reminding you of what Gauss's law is. Gauss's law was a convenient way to relate the sources inside of a volume with the electric flux lines that are on the outside, which is to say that if we have some closed volume and we had inside, we had little electric charges, then we said that the divergence of the electric flux line D equals the charge density rho v that is at any given location. And this we call Gauss's law. Right? It's a fancy way of saying that electric flux lines emerge from positive charges and converge into negative charges. That's all Gauss's law really says. The equivalent for magnetic fields, I'm just going to draw this little thing here just to show that this is a three-dimensional surface. The equivalent for magnetic fields is called Ampere's law, and Ampere's law told us that if I have currents running through this surface, and that's going to relate to magnetic fields that are around the outside of it. And so Ampere's law is written in the following form, that the curl of the magnetic field equals the current density J. And this is called Ampere's law in differential form. And this is much more useful than the integral form that we covered in the last lecture. So all it really tells us is that anywhere in the universe where we've got some amount of current flowing in a certain direction, we're going to have field lines that are going to have to swirl around that current. And the way you determine that is with the right-hand rule. You can take your thumb and point it in the direction of current, and the curling, the curl of H is going to show you the way the magnetic fields are swirling around that current. And that's called Ampere's law. All right. And again, these are nice contrast to each other because Gauss's law has to do with the fact that electric field lines are emerging from or converging into positive charge. And Ampere's law is a much different notion that field lines are swirling around currents. So they are different and sort of complementary to each other, which kind of makes sense because as we talked about in the last lecture, when we contrasted divergence with curl, they're essentially opposites of each other. That if you are swirling around the location, you are not diverging or converging. You're not moving away from it at all. And on the contrary, if field lines are converging into or diverging away from, that's the opposite of spinning around a certain location. So they are very much opposites of each other. All right. So this use of Ampere's law is in general much more convenient than the integral form, because unlike the integral form, you can do something like divide up space into little 3D voxels. Can't draw that very well. You can divide up space into little 3D voxels and solve this in a differential form, meaning if I have two consecutive cells and I've got a value of hx over here and a value of hx over there, and let's say this is the y direction, then let me just draw this out a little more exactly. Here, let's try it this way. Let's say this is hx 0.1, and this is hx at 0.2, then an approximation of dhx dy, we're taking this to be the y direction, is going to be approximately equal to hx point number 1 minus hx point number 2 divided by delta y, or that separation there is delta y. So we can make approximations to derivatives pretty well. All we've got to do is split space up into small little squares or small little cubes and solve a derivative as a difference between consecutive cells. So that concludes this relatively short lecture on Ampere's law and in a differential form. And we'll move on next to continue to develop our chops in understanding magnetic fields.